This video is going to take a look at how to find horizontal and vertical asymptotes of an improper rational function. By improper, we mean the degree of the top is bigger than the degree of the bottom. Now in this case, it's only one power bigger, x squared versus x to the first, and that's the only kind of improper rational functions we'll look at in our class, even though you could look at lots of other kinds. For example, this could be x to the fifth over x squared, and that would be another example of an improper rational function. But we're going to just stay with 1 degree more on the top than the bottom. Okay, so once again we got a factor to find the asymptotes, and in this particular case we're going to go ahead and factor a trinomial's lead coefficients 1, and that's fairly easy to find then, that we have two numbers that multiply to -3 and add to +2, and that would be +3 and -1. But on the bottom we didn't need to factor in this problem. If it was factorable, certainly we would. So we do have a factor down there though, right? It just stands alone. And we now are going to go ahead and talk about how to find the vertical asymptotes. Well, the vertical asymptotes have to do with the factors of the denominator and what the behavior of the output of the function is when we get really close to dividing by 0. Now we're not allowed to divide by 0. In other words, x could not be -1 in this function. In fact, because then -1 plus 1 would be division by 0. In fact, you can see over here in the discussion of the domain that for what value would that denominator end up being 0? Well, we could solve this little equation. If you said, well, set the denominator equal to 0 and find out the values that would cause the denominator to be 0, and it would be when x is -1. So we're going to say that the domain could be any real number. X is the set of all numbers such that x cannot be -1. It could be anything else. Well, the domain and the vertical asymptotes are related, because if the domain is a value that I cannot have because it would cause my function to divide by 0, it turns out that a vertical line at that value of -1 would be a line that when the function approaches, the answer to this function would get huge, either a big negative or a big positive. And the reason for that is if -1 gives me division by 0, anything close to -1 is going to give me an answer a value down here that isn't 0 but so close to it that it would divide this overall problem by a really small value and cause the outputs to be very big. We'll worry about those specifically when we do the video on trying to graph this, but that's what a vertical asymptote indicates. It's a place where values, as it approaches that line, get really big in the positive or negative direction. Let's just go ahead though and put the line in. So when you graph x is equal to -1, it is a vertical line at -1. So we have our vertical asymptote right here on this function. Okay, now can't see that too well. So I just drew a vertical line at -1. Just straight down here, I drew a dotted line. It's imaginary because it is not a graph of the function. It's where we believe the function is going to trace itself and follow eventually when we do the other video having to do with actually graphing the full function. Okay, so now we also need the horizontal asymptotes, or in this case, it turns out when you have an improper rational function, you don't actually have a horizontal asymptote, you have what is called an oblique asymptote. An oblique asymptote is some kind of linear graph, like this or like this. And the way you find that, it's really going to be a linear equation. And it makes sense that it's going to be a linear equation because look, if you have x squared on the top and x on the bottom, for really big values, this thing starts to act like x squared divided by x, because all these other values wouldn't matter too much. If I put 100 in here, for example, 100 is not going to make much difference over here as much as it is in the squaring. So it turns out the oblique asymptote acts like really a division here and the linear equation that the x squared over x produces. Okay, so what we're going to do is we're going to go over here to some division. I'm going to use long division. I already did the work on it. And I'm going to divide the denominator of a function into the numerator and see what this, now this would still be the full function that I get out of the long division. But look it is x plus 1. Now it also has a remainder, but like I was describing over there earlier, is if you start to put big values in here like 100, you get 101. But over here, this remainder wouldn't matter very much at a value like 100 because it'd be minus 4 over 101 is a very small value. It's not going to change the answer of 101 by very much. So this function really is behaving like x plus 1 when the values get big enough. This x plus 1 is going to be our oblique asymptote. So over here I stated that our oblique asymptote is y is equal to x plus 1. And we're going to graph that line. Well, we know how to graph linear equations, so we're going to start at, if it's x plus 1, we're going to start at a y-intercept of 1 and start to count off a slope of 1 to 1. So I'm going to be right here. I want to do this kind of lightly because don't forget, these are not points on my graph. They're points on an imaginary line that our graph will approach in our later video when we actually do the graphing of the function itself. This video's intention is only the asymptotes. So I'm going to be here, I'll go up 1 and over 1, and I'm just making light marks just enough so that I can barely see them well enough to go ahead and put an oblique asymptote in there. It's going to look like this. Okay, so now what's going to happen is I'll use this same sheet on a later video when we go ahead and we do the full graph, and I'll have my asymptotes in there already.